So I see that the number of delegates has been hovering around 666. I hope that's not an indication of the way things are going to go for this talk. So I was given this topic by the organisers back in September. So the value of in silico predictions for molecular replacement and crystallography. And at the time, the topic was far less high profile than it is now. So it's been a very interesting talk to put together, actually. And I would like to thank my organisers, people who've helped me with this talk, Massimo and Randy a lot, and also special thanks to Dan, Adam, Joanna and Marcus, whose some of the results I'm going to be sharing in this talk, and also many thanks to the contributors to CASP 14. So, X-ray crystallography, I'm going to divide it up into 5 steps. First of all, you need your pure protein, then you need your crystal, then you need your diffraction data, you need to turn your diffraction data into electron density, and then you need to trace your density to get your structure. And in between these steps, the diffraction and the density, you have, of course, the crystallographic phase problem. How do we solve it for macromolecules? I'm going to talk about 3 methods, difference Fourier methods, MR, and experimental phasing. And I'm further going to define divide experimental phasing into 3 types, SAD, MAD, and isomorphous replacement, the family of isomorphous replacement methods. Now, if you know what I'm talking about, that's fantastic. If you don't know what I'm talking about, then they're just categories for experimental phasing, and don't worry about it too much. So this is the chart of the growth of the PDB. I'm sure many of you have seen it in many different forms over the years. This is just going back to 2000, and the dark grey are the structures that are added each year. If we just take those dark grey structures and divide them up into 5-year bins, you can see the plot on the right here. And 2020 is on its own orphan year on the end at the moment. Don't panic that it's so low. It's always low at the beginning of the year, the next year, and then it gradually builds up as more structures that were deposited are released on publication later on. So these are the structures binned, and I'm going to ask the question, what is the breakdown of the entries in the PDB by method of phasing? And I've used the structure determination method entry in the PDB record. This is a free text entry. It's highly variable. I spent a lot of time looking at all the different permutations and commutations of words that people had used. So caveat, caveat, caveat on how accurate this is, but I'll show you the results. So the first thing is that unfortunately, at least historically, a lot of the records are actually null, and we don't know what's in those records. It's quite possible that it's a biased sample and that it's not an unbiased sample. So I can't comment on those. The second thing to say is that the vast majority of structures are solved by molecular replacement or difference Fourier methods. That's been increasing dramatically over the years. And of course, you can draw a straight line back from there to the start of crystallography when all structures were solved by isomorphous replacement methods. So that's to be expected. Some difference Fourier structures may be recorded as MR. I don't have any, that's just a gut feeling. I don't have any proof of that. It's just a feeling. Then if we look at the remaining structures, all the ones that are solved by experimental phasing, you can see how the proportion of SAD versus MAD versus IR has changed over the years. So 20 years ago, MAD was really popular. Now SAD completely dominates, and hardly any structures are being solved by isomorphous replacement or MAD methods. If we split that up instead into numbers rather than percentages, and that's the log scale on the right here, you can see that actually the numbers haven't changed so much. It's really just that the number of structures is going up, and all the new ones are being solved by molecular replacement. And we'll come back to these lonely little 14 isomorphous replacement structures later on. So let's take this distribution and get rid of the null, renormalize, and this is where we see that there are 80% of the structures that are solved by difference Fourier or MR over the last 20 years, but 95% are solved last year by MR. So what's MR? That's when you have an old structure, you need to rotate it and translate it until it aligns with your new structure in your new crystal form, and from that you generate phases which go on to solve your structure. Molecular replacement's a 2-step process. Well, has 2 components to it. The first is the search strategy, which is the method for exploring the poses. And you can think of difference Fourier methods really as being a no-search molecular replacement method. And then secondly, you have a scoring function, where you, this is what you use to work out when you have your old structure in the new, in the correct place in your new crystal form. And I'm going to be talking a lot about the LLG. So why has molecular replacement come to dominate? Well, it's a very, very versatile technique. You can use everything from full structures, quaternary assemblies, all the way down to single atoms. And what you can use depends on the resolution of your data. So this is the PDB again, showing it split up into resolution bins this time. And you can see single atoms, you need very high resolution data. And as you get to lower and lower resolution, you need to use more and more of your asymmetric unit to solve the structure. You can obviously use the larger structures to solve the higher resolution data, but not in the other direction. And if we look to see what the median resolution is, it's 2.2, and that's surprisingly high resolution. I think what that means in practice, of course, is that your structure will always be less than 2.2 angstroms and everybody else's structures will be more than 2.2 angstroms, because that's just the way it is. But basically it means that a large proportion of the structures in the PDB are amenable to these techniques that use small secondary structure elements, so single helices or fragments or domains and so on. And that's really been the power of the technique over recent years. So that's the MR component. Let's look at SAD. That's only 4% of current structures. MAD is languishing at 1/3%, and isomorphous replacement is languishing at 1/4% of structures. These are the magic 14 structures that last year are recorded as being solved by IR methods. And so the question I'm going to ask is, what would it take to solve these isomorphous replacement structures by molecular replacement? And the answer, of course, is good models. And unless you've been living under a rock, I'm going to be talking about AlphaFold 2 and asking the question, can AlphaFold 2 models replace experimental phasing? So back to some theory about molecular replacement to start with. I'm talking about the theory underlying phasor for MR. We use the scoring function, the LLG. And to get a signal in our molecular replacement search, we need approximately 10 LLG units per degree of freedom. So in space groups where there are 6 degrees of freedom, you need 60. In polar space groups with 5, you need 50. And in space groups where you need 3 degrees of freedom, you need 30 LLG units. That's related to the TFZ score. If you're a user of phasor, you will know about the TFZ score. If you're not a user of phasor, don't worry about it. Just concentrate on the LLG score, which gives you all the information that we need for this talk. So the LLG is just the scoring function for molecular replacement, but it's based on this maximum likelihood understanding of molecular replacement and SAD phasing as well in phasor. And the power of that technique is really that it gives you lots of statistical tools, not just the scoring function. One of these other statistical tools it gives us is the expected LLG. And that means that in advance of doing molecular replacement, we can work out what the LLG would be for approximately what the LLG would be for a correctly placed solution, just from prior knowledge that we have about the model error, the data, and the total number of reflections that we've collected and so on. So it's a prediction method that helps us understand what the LLG will be when it's correctly placed. Not obviously we haven't solved it yet, but we will know when we will have the correct answer what it would be. And you can see here on the right, if we break down what it's based on, our model errors are based on the completeness of our model and the RMS error of our model, and our total number of reflections depends on the resolution and also some parameters of the space group and the unit cell. So these are the things that determine our LLG and our expected LLG, in fact. And key amongst this is our RMS error. So what's the RMSL of the RMSD of the AlphaFold models? Well, it's really, really good. So these are derived from the CAS4 website, downloaded the RMSD all parameter and plotted that for all of the AlphaFold 2 models. And you can see it's ranging between 0.8 up to, well, higher than 10, but the bulk of them are basically in the range of 0.8 up to about 3.2. That's for all. There's another measure that you can get access to on the CAS14 website. That's an LGA sequence independent superposition RMSD. That's based on C alpha atoms, and that's even a tighter distribution. So that's between 0.4 and 2.4. So it's really, really tight. And just to give you some degree of context, structures solved in different crystal forms have an RMSD around 0.4 angstroms between background atoms. So I'm just going to bin these so you can see the zones. We've got 0.4 to 8, 0.8 to 1.6, 1.6 to 3.2, and then greater than 3.2. And that is what we're going to use for our prediction on what we would need to solve these structures by isomorphous replacement. Okay, so these are the numbers when we calculate them. So there's a few things to look at here. The first is that the RMS error, our LLG goes up as our RMSD goes down. That's obviously what we'd expect. I'm just going to resort this column by the LLG for 0.4. There we go, sorted and then coloured in. So in green, we have here all of the structures that have predicted to have an LLG greater than 60 for the monomer. And you can see that the margin for error is really low. So you really do need good models in order for these molecular replacement to work with these structures. But that's within the range that we're getting with the alpha-fold 2 structures. The other thing to notice is the resolution. So broadly speaking, the LLG goes down as the resolution goes down. And the other thing to notice is the completeness. So broadly speaking, the LLG goes down as the number of copies in the asymmetric unit goes up, which means that each monomer is contributing a smaller proportion of the scattering, as you're searching for that particular monomer. So that's all sort of expected behavior. So the point to make here is that, if you have a really, really good model, even a perfect model, then molecular replacement can still fail, not because there's a problem with your model, but because there's a problem with the crystal form. So that's, you haven't collected enough data, the number of copies in the asymmetric unit is very, very high, or you've got a unit cell and space group that just means that you're getting very low numbers of reflections and so on. So with good models, the problem, you could argue the problem's flipped, actually. The problem is with the crystallography rather than with the model. How did we get to where we are at the moment? Well, I credit where credit's due. The first structure to be shown to be able to be used for molecular replacement was a Rosetta model from David Baker's group back in CASP 7, 2006. This was a proof of principle though, because it was a retrospective study. It wasn't solved for real. CASP 14, of course, we're now past that, and molecular replacement models are being solved. Structures are being solved for real with these de novo models. 3 of them were solved as part of the CASP 14 challenge. And in addition to that, there are also 2 of the structures in the CASP 14 challenge that were helped along considerably by the alpha-fold 2 models. One, in that the monomer predicted a monomer structure not evident in the crystal form, and in another case, it actually fixed a tracing error in the model, in the crystallography. And the other interesting thing is that these structures commonly diverge from the alpha-fold 2 models, mainly at the crystal contacts, which I think is telling us something really interesting as well. So the high accuracy assessment for CASP 14 was done by Marcus and Joanna in collaboration with Dan, Ronan, and Adam. The analysis used for these scripts, used for this were originally written by Gabor, who's an alumni from our group. And I really recommend that you go and look at Joanna and Marcus's presentation on the CASP 14 website, and also Dan Rigdon's presentation on the CASP 14 website, and in fact any other presentations on the CASP 14 website, because they are all really, really interesting. I want to just home in on one of the parts of the high accuracy assessment that I think illustrates a point I want to make really well. So this is the T1024 data set. This is data prepared by Marcus and Joanna did the figure here. This is the structure shown on the right. And what this test is all about for molecular replacement is that you take your target component, which in this case is domain 2 of this 1024 structure. And so let's say that's the one in blue. And you put the background for the search in, which is in green. So this is if you had a partial molecular replacement solution. And then you look to see how the LLG is changing as you add the next component to your search. So this is trying to mimic a molecular replacement search, but it's not a full search, it's just superposing the structure and seeing how the LLG changes. So that's you can see that the bar chart on the right is trying to illustrate what I mean by this thing. And you can see that the alpha-fold 2 models, as in many other tests, are outperforming the other structures. And that it's interesting, it seems to be a sort of exponential type behavior here. It's plotted on an LLG scale as well on the right here. So the question is, why does the plot look like this? So on the bottom here, we have it plotted against the high accuracy global distance test. And we can show that these structures now are getting so good that the GDT-HA and the RMSD are actually highly correlated. So the GDT-HA is the high accuracy test that tells you what proportion of the residues in the structure are within a given cutoff. This is the high accuracy one, so it relates to things that are less than 4 angstroms. And it's an average of various parameters. So we can show that that's correlated with the RMSD. Now we know that the expected LLG is proportional to the sigma A to the fourth, in fact, as approximately. And we know that the sigma A is an exponential on the RMSD, proportional to an exponential on the RMSD. So we have all of these components. We can see the relationship between our expected LLG and our RMSD. And if we plot that, you can see the behavior is not actually exponential, it's exponential on RMSD, but the plots really follow the theoretical expectations for the RMSD. So it's legitimate to ask the question, what's the value added of this analysis for molecular replacement over just looking at the RMSD, right? We're just increasing, as the RMSD is getting better, our LLG is getting better, that's, what we would expect. And if I can answer my own question, the answer is that it tends, the molecular replacement score also captures the information about the accuracy of the error estimation that the participants have to give as part of their modelling procedure. So CASP-13 clearly showed the importance of the prediction of local and global model accuracy when it came to molecular replacement. This is where you put your model accuracy and your B factors. And that was confirmed in CASP-14 here. So this is really the question du jour. CASP-14 three structures were solved with AlphaFold 2. How many other CASP-14 structures can be solved with these AlphaFold 2 models? So the ones that were solved are in green and the others are sitting here, right? So for this, we use Phaser Voyager. It's our new pipeline in development, hopefully soon to be released. It uses a reconfigured Phaser TNG codebase, which we've first paper in the first issue of 2021 Acta Christi. You go and look at it now, it's available online. I got the email yesterday. And then we also set the VRMS to 1.2 angstroms and then refined from it. And for a full discussion on what the VRMS is and what you might want to set it to and all the problems associated with it, there's a paper by Kaushik last year. It also then uses an ensemble correlation analysis, which is a new analysis that's yet to be published by Massimo, coming soon. It also uses statistical trimming, again, that will be published by Massimo soon. It also, if a pose is found by one model, other models are superimposed in the same way and scored in order to work out which one of those models is the best. And that's from an idea originally by Gabor, implemented his MRAGE pipeline. MRAGE, sorry. If a structure is available, then we check the solution with Phoenix.famous, and the information for that is in the computational crystallography newsletter. And then at the end, we auto build with Phoenix to give an initial value and R3 just to confirm that the solution is correct. Auto builds published by Tom Twilliger. Right. Yes, the other thing I wanted to say was that the molecular replacement trials were performed as part of the CAS-14 assessment by Dan, Adam and Ronan, not by us. So we as non-assessors, we didn't have access to all of the data, and we're very grateful to those experimenters who did make their data available to us. So 3 of the results that I'm going to show are not ours, they're the results from the AMPL pipeline results. So take your bets. How many? 33.5 can be solved with the AlphaFold 2 models. I'm going to talk about 3 of these. These are results generated by Massimo over the last 2 weeks, since just before Christmas. Really phenomenal effort to get it all done. We've all had a very busy Christmas, but since we've had nothing else to do, then crystallography is a good thing to fill the time. Right, so the 3 structures I want to talk about are this complex structure, crystal structure number 3. So in pale green here, you can see most of them were solved with just Phaser Voyager defaults, either ensembles or single models. One was solved by Archambault Light on coiled coil, so it wasn't actually an AlphaFold 2 structure, it was just a coiled coil structure. One was Shredder, and then this polymerase structure. So this is the one that's really, and I'm part of my problem is I don't really understand what CASP is trying to do here. So these are single chains, and they've split them up into different numbers of residues, and they've put them as different models in the CASP challenge. And so you work with what you get. So I'm trying to rebuild up the structure based on all of these fragments that have been generated by the modeling. and I can get halfway there. So what's here, the A, B, C, D, F, G, that's the order that they went in. If they lowercase, they were put in by symmetry, manually putting them in as symmetry copies as part of the pair rather than actually by molecular replacement search. And star means that I did a ref-mac refinement between the end of that and searching for the next component and so on. It might be possible to get more out of there. I actually doubt it, because looking at those other models, they are quite divergent. So I think that would be unlikely to stall at that point. However, I looked at the anomalous data that was present in the MTZ file that I was given, and it easily dropped out the selenium sites in that file, and the map looked really good. So, you know, MRSAD would have taken you from there. The other one, 1032, that was one that you can see it's really quite a flexible structure, and this one was solved by taking component shredded models, as we call it, from the original structure, and then using those in pieces to build the target up in small components. And then finally, this is one that wasn't solved by the AlphaFold 2. It was solved by Archimboldo Light on coils, and that was a clear solution at the end. So the to-do list. First of all, we need to get access for the models. Secondly, we need to optimize the models, the error models, to get the signal. The other interesting thing about these models is that the trimming on the loop regions doesn't work in the same way as it does for experimental models, where the loop regions vary a lot. In the AlphaFold 2 models are really consistent in the way they think, what they think the loops look like, and that is a challenge because they can be wrong. The jury's out on whether the difference actually is between the models or whether it's actually to do with the structure itself. And there's a lot of searching that's required in these, so, you know, tracking and tracing and looking at persistence is important. So let's go back to our 5 things. I've talked about the phase problem. I'm expecting even more structures to be solved by molecular replacement, and you know, I think the approach will be, if it fails, give me another model. Just throw another model and I'll try that until something works. I think experimental phasing will become a niche method, and I think isomorphous replacement may actually go extinct. But there are other problems in this pipeline as well. You know, there's the crystallization problem at the front. How can that help us here? Well, we have improved design of constructs for crystallization. You know, interestingly, we can also discern how the structure is distorted by the crystal lattice contacts, you know, if we're trusting the model. And finally, you know, it may be possible to model the crystal, not just the monomer, and that may be interesting in the context of trying to model interactives rather than just single structures. So another pinch point is getting good data. I think one way you can look at this is the data could be worse than it would otherwise need to be to solve the phase problem, because in a sense, the data only needs to verify the model. And I think XFOL data might become easier to do structural biology with, because you know, if you're looking at solving XFOL data with molecular replacement, then that's going to be a lot easier going forward. And then I'm going to paraphrase, this is the R factor less than 20% problem. If you want to shoot me for putting it that way, you'll have to wait until the end of my talk. But the refinement will often start from complete models, the reduced need for density modification and de novo model building. And possibly there'll be increased use of MRSAD, although possibly that will be SOFSAD for difficult cases. What else? Well, this is the big question, of course. So, you know, one aspect of it is what's actually going to go forward into crystallization as a result of these models being available. And the other end of the process, what structural biology are we going to know about, by new things we're going to know about without doing the crystallography and just looking at the models up front. So I would really like to thank my colleagues in the READ group. They've been fantastic during lockdown. We've managed to keep everything going with really good and interactive lab meetings. You know, and it's been really quite a productive time. So many thanks to them for all of their help and support over the last 9 months or so. And I'd like to thank Wellcome Trust, CCP4 for funding, NIH for funding through the Phoenix, and acknowledge the Horizon 2020 program, which is Massimo's Marie Curie Fellowship. And thank you all for listening.